Alright, so let's talk about this video really quick. This is a video about a reaction called Hydroboration Oxidation, and it's another way to make an alcohol from an alkene. It's another addition reaction, except this one as its main difference is this forms an anti-Markovnikov alcohol, and as such is unique, because the other alkene addition reactions that we've seen to form alcohols form Markovnikov alcohols. So in other words, the product that we get here is where the OH, which usually adds the most to the more substituted carbon, in this case actually adds to the less substituted carbon. Alright, and if I did this properly I would have drawn that in blue, just so you can see that the alcohol actually adds here, and the hydrogen, which originally comes from the BH3, adds here. So opposite to the normal Markovnikov regiochemistry, and crap, hang on, that's just my wonderful touch at work. Okay, yeah, so opposite to the normal regiochemistry that you'd normally see from Markovnikov products, this is the one that does the opposite. Now let's just talk a little bit about the mechanism and why. It's much more simple than it might seem. So I'm going to draw out the alkene, the same alkene we have at the top of the page there. And the first part that we're going to bother ourselves with is the BH3. That's going to add across the double bond in a particular way. Now, when you look at the structure of BH3, it essentially looks something like this. It doesn't have exactly this structure, but for the purposes of this reaction, we're going to assume it does. Boron, if you remember, is one of the two elements in the periodic table that can disobey the octet rule by not having 8 electrons around it, and thus being electron deficient. This is a good Lewis acid, it can accept electrons. And so when this guy comes into contact with this, it adds in a particular way. Now ask yourself, which of these two, hydrogen or boron, which one is bigger? Now if you look in a periodic table, you'll find of course hydrogen is the smallest atom possible, so anything else is bigger than it. So when I bring along my BH3, the boron and this hydrogen in this BH bond are going to line up with this double bond here. The question is, does the boron go here or does the hydrogen go here? Well, because hydrogen is smaller than boron, the hydrogen is going to fit in the area that has less space or the more hindered carbon, and the boron is going to go where there is more space. So what that means is the boron ends up going where there's less, you call it steric hindrance, so the boron would actually end up being here. I'm just going to show it here. So it's almost like these two are coming in, kind of homing in on each other, and here's the rest of the boron there. Okay. Now remember what we said before about boron being electron deficient. That is true. So what actually happens is, if this is electron deficient, this is the electrophile, this is the nucleophile, as it usually is, and those electrons can just go down there and attack that boron. And so that means what happens here is that those electrons go down here, and what we end up with is that this bond then breaks to take the electrons to go up to here to take account of the carbocation that's just formed here. Okay, we aren't going to show the carbocation because it happens all at once, and it goes through kind of a 1, 2, 3, 4-membered transition state, and that's illustrated in the book, but I'm not going to go through that. So these electrons from this bond go up to this carbon, and by this carbon I mean this one, and so what we end up with is an intermediate that looks something like this, where the boron has added on one carbon, And of course on that boron are the other two hydrogens, this one and this one, and then over on this carbon I have this hydrogen. And these add in syn stereochemistry. In other words, they add from the same side of the molecule. You remember for the halohydrin and the halogenation, the two groups added anti to each other? Well, here they're syn, they're on the same side, so they could both be wedges or dashes. And essentially this is the mechanism of that first step. The second step, virtually no textbooks go into the mechanism. As far as I'm concerned, it's beyond the scope of the course. It's not something that we have to worry about. And if I was to go into it, it would just be confusing. Essentially, this is an oxidation step. The BH3 group here, or the BH2 I should say, gets removed and displaced by this OH group with something called retention of configuration, meaning if this was on a dash and this was on a dash in this intermediate, then the OH would be on a dash too. So retention means it keeps the same stereochemistry. So if this is on a dash, so is this. So these two end up both being on dashes. That's why this is syn addition. But the important thing is not so much the syn addition, the fact that we have anti-Markovnikov regiochemistry, and that's what makes this reaction unique. So if I was to say something like this, and I was to give you this reaction, and I was to say, well, okay, here are the products, or here are the reagents. First one is BH3 and THF, and by the way, THF is just a solvent, it's just an organic solvent that this first step happens in. And then we have hydrogen peroxide with OH minus present as well. And I'll ask you to watch the structure of the product. Well, what you'd hopefully recognize is in the BH3, the B would go here, the H would go here, you'd have BH2 here, and then the OH minus would come in and displace it. But more importantly, you would have the anti-Markovnikov alcohol. It's the only reaction we know of to actually make that product. If we were to do, say for example, H3O plus and H2O here, we would, through the mechanism that we've seen before, we would get the most stable carbocation being on this carbon. We'd end up with the Markovnikov. So this is the anti-Markovnikov product, and this is the Markovnikov product. And that's what makes this hydroboration oxidation unique. It's the only reaction that forms the anti-Markovnikov alcohol.